now let's look at some how do you implement this, and the framework of choice for us in this tutorial is PyTorch. PyTorch is quite popular right now, and there are, I mean, you can go to any, whether it's Stack Overflow or whether it is which are the frameworks researchers are using to write their neural network code. It turns out that more often than not it is PyTorch. Although there are other libraries like TensorFlow or Yax, but right now this seems to be very popular, and this popularity also comes from the fact that it is quite modifiable, quite easy to debug, and all that, right? So, so for you to import, for you to use PyTorch, you would have to import it, and the library name, how do you import that is import torch, and torch dot version would tell you what is the version of it. This is what I am operating on right now. So one central concept to this PyTorch is this entity called Tensor, right? So you would be familiar with how would the differentiation between a scalar, a matrix, a vector, matrix, and a tensor. Right, this is some single real valued number. This is a combination of real valued numbers, and this would be a higher dimensional, let's say this would be higher dimensional matrix like 2 by 3, where again these are again scalar values here, and this could be a higher dimensional matrices. This is what are scalar, vectors, and tensors, and these are the basic building units of any neural network in PyTorch. You can represent any data using these tensors, and let's say tensors have some dimensionality to them. In this case, the dimension of this particular matrix is 2 by 3, right? And so one simple example that I can use to motivate this is this image, right? If this was a grayscale image and there are 224 by 224 pixels, each pixel has some value associated with it, and that is good enough. This matrix 224 by 224 matrix would represent each pixel and hence the image. Now if there were, let's say, if that was grayscale, that is good, but if it is a color image, then there would be RGB, 3 channels in this case, and so there would be 224 by 224 and 3 such matrices, right? And using this tensor, I can represent a color image of this sort, and underlying you can see that each of these values would be some number, real value number, right? So you can go from input an image and you can represent it as tensor. And doesn't matter what is the what the modality is, that everything would still be a tensor, has to be represented as a tensor, whether it be image, whether it be text, or whether it be video, right? You have to figure out some way to convert this that mode into some vector or tensor representation of it. Right. So start with some basics of it, like how do you create tensor in PyTorch, right? So the syntax turns out is that torch.tensor would allow you to create scalars or matrices, vectors, or tensors, right? So here you are creating a scalar, and you can use this syntax to find out how many dimensions are there. Since this is a scalar, there are no dimensions, there is 0 dimension, and if you want to access the item, the values embedded in that tensor, you can say scalar.item, it will output this particular number. Now let's say that instead of just a scalar, you want to create a tensor, create a vector. The syntax is still the same. When you compare it with here you are just using one element, but here you are passing a list, right? So if you pass a list of numbers, it would create a vector tensor out of it, right? And if you check this dimension, dimension of this vector, it is 1, right? And like number of dimension, there is also shape. If you print a shape of a vector, it will tell you what is the exact shape of the vector, or any tensor for that matter. So this dot shape and dot dim are basically properties of any tensor object, right? So this is a syntax again to create a matrix where you're passing a list of list, right? A list would create a vector and a list of list would create a tensor, right? If you check the number of dimensions, you can say that since there are rows and columns, there are 2 dimensions and hence 2. And if you print the shape, you can say that the shape of this matrix is 2 by 2. If you create a 3 by 3 matrix, it will be matrix dot shape will give you 3 by 3. And building on going to the next level, you can pass on a list of a list of a list and you can create a tensor. Here the number of dimensions are 3. It's a 3-dimensional tensor and the shape is 1 comma 3 comma 3, right? And if you want to create a you can let's say create something like this, and you can say that the tensor shape is 2 comma 3 comma 3. Here it had only 1 element, but in the outer dimension here there are 2 elements, right? These are the 2 elements, that's why 2 comma 3 comma 3. So another way to visualize this is could be this, like each bracket will tell you the number of elements or the values in that shape, right? Moving on. So in all the previous cases, you were explicitly mentioning what are the values in each of these positions, right? You're saying that the first element is 1, the second element 2, the third element is 3. But when you are especially working with very large tensors, you don't have to specifically mention what are the exact values in each position. So a slight callback to what we were discussing during training of neural network. We said that when we are just starting the neural networks, all these weights are randomly initialized. All those weights, when you start out, they could be zeros, there could be ones, or they could be randomly initialized, any value between 0 and 1. And for you to create that, the syntax is again very simple. You say torch.rand and you mention what is the size of the vector or of the tensor that you want, and it would automatically create a tensor which is randomly initialized. And this is quite important when you are especially initializing, let's say, a neural network, for example. And yeah, this is here we are just initializing a slightly bigger 3-dimensional tensor. Like you were initializing a tensor using random numbers, you can do the same. Let's say initialize a tensor with zeros. And all the elements would be zeros. You can also ones, where all the elements are ones, right? And you can, like, you have functions like range, arrange in NumPy and simple Python. You can use that to create tensors as well, right? So tensor.arrange start and each step, so it automatically creates a tensor of 10 elements where start is 0 with an increment of 1, and you end up creating 10 elements. Okay, so here, if you had noticed, we were also we were also printing what is the D type of a tensor, right? So like there was a dimension and a shape associated with the tensor, there is also a D type, which is essentially data type associated with the tensor. So when we print data type, it says torch.float32. Let's take a closer look at what does it mean. So anybody knows simple programming, you can probably appreciate the fact that there are data types or data classes in a programming language, like an integer, a float, a character, so on and so forth. Similarly, in a tensor as well, you can choose a specific data type, right? So there are many data types that are available in PyTorch. You can access that particular list here, but one particular D type or one family of D types that I would like to cover here is a distinction between FP32, FP16, bfloat16. So you can looking at these examples, you can see that the number of bits used to represent FP16 is much lesser than FP32. What is the advantage? So this takes 32 bits here, it takes 16 bits here. That's why in the name FP32, FP16. So the point here is that this takes higher memory, but it can have a higher precision. It could represent much smaller, much bigger numbers, whereas FP16 is limited in its precision, while it consumes a smaller memory as compared to FP32, right? So while you need let's say 32-bit floating point if you want a higher precision in your network, but it also comes at a certain memory cost, right? So you can choose between these two depending on how you want to create your network, right? And that's what d-type dictates, right? And you can go to this particular link and you can find out what are the different data types that you can create in PyTorch. 32-bit floating point, 64-bit floating point, 16-bit floating point, 30-bit. You can create a complex number, you can create integer using 8-bit integer, 16-bit, 32-bit. So the difference between this 8-bit or 16-bit is what is the range that you can represent using these using this data type, right? It would be smaller if it is 8-bit, it will be larger for if it's a 32 or a 64-bit. That's the only difference, right? And this would give you a comprehensive list of data types that you can create in PyTorch. So while you are creating a tensor, you can also mention what is the data type that you want. So if you do not mention anything, it defaults to torch.32. But if you want a control over what is the data type, specific data type being constructed, you can just mention that as an argument. Right. One more element that you can see here is this device. So as you can probably understand or probably know, is that GPUs allow for faster training of neural networks, right? GPUs are very good at matrix multiplications, and since neural networks boil down to its basics essence is just a series of matrix multiplications and some other function on top of them, they are very, very quick when you do it them on hardware like GPU, right? And you can specifically mention whether this tensor or this particular object, whether it should be occupying memory on GPU or whether it should be occupying memory on RAM or your CPU, right? So if you do not mention anything, by default it will go to CPU. But if you want to mention GPU, you can also do that, right? And this torch.good is usually the way to do that, right? One more associated argument here with the tensor is whether it requires grad or not. Grad means gradients. If requires grad is set to false, that means that particular parameter, this particular element, will not be trained as part of the network. It will not be part of the, let's say, computational graph. Whether if you want this network to be learnable, that means it gets adjusted as part of your network training, you should set this to true. Right? That's what these are some of the auxiliary flags that are associated with creating a tensor. We have already looked at shape, d-type, and device. So once, let's say, you have created the tensor using whatever syntax that you use to create a tensor, you can access its shape, d-type, and device using the syntax. You can print the tensor itself using like a simple print statement. The size is tensor shape is this. That d-type is torch.float32, and that the tensor is currently sitting in CPU, that is RAM. Right. Now that we have looked at how do you create tensors, what are the various ways of creating tensors, and what are the different attributes associated with those tensors. Now let's look at some basic operations that you can do on top of these tensors. Simple mathematical operations like addition, subtraction, multiplication, division, or a matrix multiplication, right? So if you have a tensor like this, which is basically a vector, right? It's a one-dimensional vector, and when you say tensor.10, it does an element-wise addition, which 10 is added to each of these elements. Same is the case with the multiplication. If you say tensor.10, each value is multiplied by 10. Same is again the case with the subtraction as well. Right? One important thing that you should note here is the difference between element-wise multiplication and a matrix multiplication. So torch.multiply followed by tensor and a scalar would do a element-wise multiplication where each element is multiplied by that particular scalar. Whereas matrix multiplication is matrix multiplication that you probably remember from your linear algebra class, where the difference between element wise multiplication is that this is each element is multiplied with its corresponding element. So this is what element wise multiplication is, and the matrix multiplication is that you associate a row with a column and so on and so forth, right? So you would probably also remember from your linear algebra class that while doing matrix multiplication, not the element wise multiplication, but actual multiplication of two separate matrices, the inner dimensions have to match. Okay? You can't multiply a 3 by 2 matrix with a 3 by 2. You can multiply a 2 by 3 with a 3 by 2 because their internal dimensions are matching, right? Same is the case with 3 by 2 with a 3 by 2. So the output of this matrix multiplication will be a 2 by 2 matrix, and the output of this matrix would be 3 by 3, right? Again, for you to do a matrix multiplication, the inner dimension should match. So the way to do matrix multiplication like that is torch.matmul matrix multiplication and give the arguments of tensor and tensor. If you do tensor multiply this star tensor, this does element wise multiplication. The distinction is showed in this example here. This is a element wise multiplication. You started with a vector of 3, you end up with a vector of 3 if you are multiplying tensor with a tensor. But here you are multiplying two tensors, and you see that you will get one single value of 14, right? This is the math that goes behind. Yeah, again, as I said, if you have to multiply two matrices, their dimensions have to match, their inner dimensions have to match, and this makes for one of the most common errors in any deep learning framework, where you're trying to do a matrix multiplication but their dimensions don't match, right? So tensor A, tensor B here are both 3 by 2 cross 3 by 2, and when you try to multiply them, you get this error saying that mat1 and mat2 shapes cannot be multiplied. Their individual shapes are these. Right. So that's where you can use a transpose. So transpose of, let's say, 3 by 2 would give you a 2 by 3 matrix, and you can use that to multiply two matrices, right? So tensor A here is 3 by 2 and tensor B transpose here is 2 by 3, and you can use that to do a matmul, right? So this will not give you an error because you're doing a transpose and then multiplying. Again, another way to do that would be MM is same as matrix multiplication. So this visualization will give you how matrix multiplication happens if you are interested in it. Right. So as we were discussing earlier, that there are linear layers which essentially just do that. They take some input X, multiply with some matrix A, and add a bias B. Right. And if you look at it internally, all it is doing is some matrix multiplication, some element wise addition, this is what happens in a linear layer. But again, this behavior would be different for different kinds of layers. If you know the theory of neural networks, you can see that, you can probably recall that there are different kinds of layers in a neural network. There could be RNN, there could be a CNN, and this make for different layers of a neural network where underlying operations are very different. Right. So yeah, a linear layer, you can say that in features are 2, out features are 6, and you can say that input, if it comes 3 by 2, there are 3 by, the input matrix is 3 by 2, the output would be 3 by 6, because you're saying that input would have 2 features and the output would be 6 features, right? That's what you're doing here. And again, if you boil down any neural network, you can see that it would just be a series of matrix multiplication, and over and top of that you do some more computations. But matrix multiplication forms some very, very basic components of most occurring common basic components of neural network. Alright, a few more operations that you can do on tensors. You can use min, max, mean, and sum to find out some aggregate numbers, or finding out some distribution, some numbers which reflect the distribution of that tensor. And again, the syntax for changing a D type. So let's say that you created a tensor type of float 32, you wanted to convert into float 16 or float 64, you can just say tensor.type followed by the type that you wanted to get converted. So this is the typecasting that you can do between tensors. Okay. Same is the case here. One more operation that comes quite frequently in neural networking code is that, or in PyTorch neural networking code, is this idea of converting the shape of a network, right? So let me show an example and probably that helps you. So here we created some tensor, which is a vector, and it is the size of it is just 7, right? And for, let's say, for some particular use case, you wanted it to convert into uh, into a matrix of size 1 comma 7, right? So you have a vector of 7 and you want it to convert into a matrix of 1 cross 7, right? So the syntax that you can use to do this operation is reshape. So you started with a vector of 7, and by saying x dot reshape 1 comma 7, you have converted the shape to 1 comma 7. So one thing to note here is that this is possible when the reshaped and the original matrix have the same number of elements, right? Here also the elements were 7, here also the elements would be 7, right? You can do reshaping as long as this base necessity is met, right? You can't start with a tensor of which has 7 elements and convert into a tensor which is having 10 elements, right? Because where are these other 3 elements coming from and what are their values, right? So this would be error. Okay, and there are few more functions associated with this idea where you reshape, view, stack, squeeze, unsqueeze, permute, and you can look at the documentation for these and try to understand what are they used for and what are the underlying functionality that they do, right? But the basic essence is that you can use them to change the dimensionality of a matrix or change dimensions as per the needs of your network, right? One more concept that we should cover here is indexing. Let's say that you have a big tensor like this, you want to access a particular row or a particular column or a particular let's say just a single value, right? So you can do indexing like this. Let's say you have a tensor like your tensors is a 1 comma 3 comma 3 3-dimensional tensor. You can access any of these elements using these, right? So 0 of 0 of 0 would capture this element, 0 of 0 would capture the first this particular row, and 0 would capture this whole matrix, right? You can again use notation like this to access a particular row or a particular field or a particular element instead of using this notation. Again, this notation is maybe familiar to you coming from NumPy, right? You can again convert NumPy plays very well with PyTorch. You can convert a NumPy array to a tensor. You can convert a tensor to a NumPy array because tensors have certain additional let's say additional attributes associated with them, and if you don't need them, you can pretty much do the same thing with NumPy. So you can convert tensor to a NumPy and a NumPy array and NumPy array to a tensor, right? So again, I recall to a concept that we discussed a few minutes back where we said when we start a neural network, we instantiate the neural network weights randomly, right? So that means that if I'm creating those, the values of them are randomly chosen, and if I let's say do the same process n number of times, each time I'll get different set of values, right? There's no guarantee that they are not the same all across all these n number of times. So if that is the case, it sort of makes sense that if you run your network once, you get one value. If you run the network again, you get a different value, right? Because there is randomness in the whole network. But this is sort of an impediment if you're trying to if you need your model to be reproducible in the sense that you run the model now, you get the same value. You run the model, let's say, in the second time, you get the same value, or you run the model in your system, you get some output, you share the model with somebody else, they also run this model in their system, and they should again get the same value, right? This is what we mean by reproducibility. And how you can force that is using this notion of seed, right? This random seed could be, this could be any number. So a different seed would give out different outputs, but if the seed is same, the output of that random process would be the same, no matter how many times you run, right? So if you're creating let's say a tensor using some random using the syntax torch.rand, and you're saying that you always create this with this particular seed, right? Then no matter how many times you do it, you end up with the same matrix, right? But otherwise, if you had not set this torch.manual seed with a particular seed value, these values would have been very different across two different runs. All right. So as we said that PyTorch and neural network training runs very quickly on GPUs as compared to CPUs. So this is a Google Colab notebook where you have access to some GPU if you want, without any cost. So again, the underlying drivers are NVIDIA cards, NVIDIA graph GPU cards, and this basically NVIDIA-SMI tells you what is the card you have access to and what is the size of that card, how many MBs of VRAM you have in that card, right? So I have here access to a Tesla T4 card, which is nearly 16 GB, right? So if you want to check whether you have an access to GPU or not, you can simply use the syntax. Torch.CUDA is available. So CUDA is basically a package that allows you to leverage CUDA's drivers and code that allows you to leverage GPU for the kind of PyTorch code that you want to write and train neural networks, right? So torch.CUDA is available. If it is true, that means that you have access to a neural network. So if you have access to a GPU on which you can train a neural network, if it says false, that means that you don't have a GPU. You have to do these operations on CPU RAM. So so usually you can whenever you're writing code, you should write it agnostic of whether you have a GPU or not. And one way to do that is this, where you say if CUDA is available, the device name is CUDA, if otherwise the device is CPU, right? So this device value would stay constant throughout your script, and this was change depending on whether you are running code on GPU machine or on a CPU machine, but your code will nonetheless run, right? This is better than hard coding saying that device is equal to CUDA. Let's say you also more often than not need a machine where you have more than one GPU, and device count will tell you how many GPUs you have access to. As I said previously, you can like you were able to change the data type of a tensor, you can also change the device of a tensor, whether the tensor is sitting on a GPU or a CPU, right? So code for here you can see that you created a tensor, you did not explicitly mention any device, so by default it was sitting on CPU or RAM, and you can access the tensor and the current device on which it is sitting. So it says that currently it is sitting in CPU, and if you want to move it to whatever, whether if CUDA is available to you, if GPU is available, and if you want to move it, you can just say tensor dot to device, and the device is coming from this piece of code that you have written, right? So again, by using this to device along with the combination of this syntax, what it allows you to write is a code that is agnostic to the underlying hardware, right? It is device agnostic code. It can run on CPU also, and GPU also doesn't break, right? Yeah. So so if you want, if a tensor is sitting on GPU and you want to move it back to CPU, you would have to use certain syntax like this, and yeah. So you can see that. So when this tensor is sitting on GPU right now, and you directly want to convert it to NumPy, this would give out an error. Can't convert. And so this is the error that's saying that any tensor that is sitting on CUDA, we can't convert it into NumPy, right? So you instead use tensor.cpu to copy the tensor to the memory first, right? So that's what is happening here. You're taking a tensor that is sitting on GPU, bringing it to CPU memory, creating a copy here, and then converting them into their NumPy equivalent, right? Whereas the original tensor is still sitting on the CPU, you're creating a copy using a syntax like this. Right, so this wraps up the fundamentals of PyTorch as a library. In the coming tutorial, we will look at what are the workflows that are central to PyTorch and how can you train a neural network, simple classification neural network using PyTorch. Thank you for listening to this session.